In this video, we are going to discuss how to calculate electric field at a point due to a conducting spherical shell using Gauss's law. Question 2.55. A 6 nanocoulomb point charge is located at the center of a conducting spherical shell. So we call this charge as Q, and magnitude of Q is -6 nanocoulomb. The shell has an inner radius of 2 meter. So this is my inner radius. We call this R1, and an outer radius of 4 meter. We call this R2, and a charge of 7 nanocoulomb. So the charge on the shell is 7 nanocoulomb. In part A of the question, we need to find what is electric field at R equal 1 meter. So we need to find what is electric field at this point, a distance R from the center. Since we are going to use Gauss's law to solve this problem, we will first construct a Gaussian surface passing through the point a distance r from the center. So here we construct a spherical Gaussian surface, and I'm going to find what is the electric field at this point because of the whole system. According to Gauss's law, the total flux through a closed surface is numerically equal to the charge enclosed by the surface over epsilon naught. And from the definition of flux, we can write phi as integral E dot dA. The double integral sign because the area vector is two-dimensional, and the circle over the integral because we are taking this integration over a closed surface. So this is equal to charge enclosed over epsilon naught. Now we are finding this flux over our Gaussian surface. So this area is the surface area of the Gaussian surface. And we know that surface area of a sphere is 4 pi r squared. Whereas the charge enclosed is also the charge inside the Gaussian surface, and for us it is the charge negative q, which I'm going to just write as q for now. The negative sign we can take when we are substituting the value for q. So I get integral over the entire area as E 4 pi r squared equals q over epsilon naught. Now rearrange the term to solve for E. We get E equals q over 4 pi r squared epsilon naught. Now if you notice this expression, this is nothing but electric field at a distance r due to a point charge q. And we know that 1 over 4 pi epsilon naught is equal to the Coulomb's constant k, which we can substitute here in our expression and rewrite this as kq over r squared. Now let's find the value of electric field. K is 9 times 10 to the power 9. The charge Q here is -6 nanocoulomb, and the distance R is 1 squared. That gives me the magnitude of electric field to be equal to -54 Newton per coulomb. The only reason we have electric field in the hollow region between the spherical shell is because there is a charge Q present at the center. If this charge was not present in the center, electric field at a distance within the hollow region of the shell would have been equal to 0. But since we have negative q present here, this is the magnitude of my electric field at a distance r equals 1 meter from the center. Now let's discuss part B. In part B, we need to find what is electric field at r equal 3 meter. Now 3 meter is between 2 and 4 meter. That means this point lies within the conducting shell. And we are going to follow the same step to calculate electric field at this point. So let us construct our spherical Gaussian surface within the conducting shell. We know that electric field inside a conductor has to be 0 because even though there is a charge present in the center, this charge will induce an opposite charge on the inner surface of the shell. So if I have negative q here, it will induce a positive q on the inner surface of the shell. So that will neutralize the effect of the charge at the center, whereas the charge within the shell will arrange themselves on the outer surface of the shell, creating a net electric field of 0 inside the shell. So at any point inside a conducting shell, electric field has to be equal to 0. Next, we look at part C. In part C, we need to find electric field at a distance r equal 5 meter. So this distance lies outside of the spherical shell. We will construct a Gaussian surface passing through the point at a distance 5 meter from the center, and we follow the same steps to calculate electric field. According to Gauss's law, the total flux through a closed surface is numerically equal to the charge enclosed by the surface over epsilon naught. And from the definition of flux, we can write phi as integral E dot dA, that is equal to charged enclosed over epsilon naught. Again, we are finding this flux through our Gaussian surface. So this area has to be the surface area of the Gaussian surface, which for a sphere is 4 pi r squared. The charge enclosed, on the other hand, is the charge enclosed by the Gaussian surface, which is the charge on the shell, plus the charge within the hollow region of the shell. So that is Q. So let us substitute this. Integrating E dot dA over the entire Gaussian surface gives you E times 4 pi r squared, where r is the radius of the Gaussian surface, equals charge enclosed is charge on the shell plus charge at the center over epsilon naught. Again, divide with 4 pi r squared to get E. So that becomes equal to Q shell plus Q at the center over 4 pi r squared epsilon naught. We know that 1 over 4 pi epsilon naught is K, the Coulomb constant. So we will replace 1 over 4 pi epsilon naught with K, Q shell plus Q over R squared. Now substitute. K is 9 times 10 to the power 9. Charge on the shell is 7 nanocoulomb. Charge at the center is negative 6 nanocoulomb. Divide by the distance r, which is 5 squared. And when you solve this, you get electric field to be equal to 0.3597 Newton per Coulomb. Now let's discuss part B. Part A is asking us what is the surface charge distribution sigma on the outside surface of the shell. Here we have a charge negative Q at the center of the shell. And this charge is going to induce an opposite charge on the inner side of the shell. So if this is negative, on the inner side, you will have a charge of positive Q. And the total charge on the shell has to be a sum of the charge on the inner surface plus the charge on the outer surface. So if I want to find the charge distribution on the outer surface, I need to calculate what is the charge on the outer surface, which is QO. So we can rearrange this term to write QO as charge on the shell minus charge on the inner surface of the shell. Now charge on the inner surface of the shell is same in magnitude but opposite in sign as the charge in the center. So Qi will be equal to minus of Q, which is equal to plus Q. So it will have same magnitude or the same size as the charge in the center, but opposite sign. So I will write Qi as 6 nanocoulomb. I need to find the surface charge distribution. Surface charge distribution on the outer surface will be equal to charge on the outer surface over the area. So charge on the outer surface is charge on the shell minus charge on the inner surface over the area. So area of the outer surface we will have to take as 4 pi r2 squared, as r2 is the radius of the outer surface of the spherical shell. Now we can substitute the value. Charge on the shell is 7 nanocoulomb. Charge on the inner surface of the shell is 6 nanocoulomb. Divide by the area, 4 pi r2 squared. That gives me 1 nanocoulomb over 4 pi r squared. So 1 nanocoulomb is 1 times 10 to the power negative 9 over 4 pi R2 is 4 squared. And when you solve this, you get the surface charge distribution to be equal to 4.97 times 10 to the power negative 12 coulomb per meter squared. According to Gauss's law, the total flux through a surface is equal to